same direction. This one closed, packed, let's say, with highest line density, which means relatively along this direction, the distance from one to another is the first closer. Second, if you compute actually just energetic reason, the barrier is much smaller compared to the other direction. The distance is shorter. At the same time, the corresponding energy to overcome from one position to another position along that direction on the same plane, but along different directions. Along those direction with highest line density, the kinetic energy is also lower. Okay, we said right in the previous case, right, if you want to deform the crystal, right, you need to think about different slip system of each grain, depends on specific orientation. So therefore, if you want to deform a polycrystalline system instead of single crystal, so you macroscopically apply the stress, for example, tensile stress here, but microscopically then you consider the different orientation in each grain. Okay, whichever you first, right, like say have high resolved stress on that plane, you'll use first. Okay, and through, for example, the conventional synthesis process or processing process before further mechanical rolling or etc. deformation, you may have the crystal that is relative isotropic. Okay, in the sense you have grain relative similar size or similar dimension on each direction, and therefore, if you try to compute the average, for example, yield stress along each direction, they are roughly the same. So it's kind of like isotropic. Okay, if you have a lot of equal-axis random oriented grains. However, mechanically, people can apply the rolling or drawing eventually to make a texture corresponding so-called anisotropic yield strength, for example, along different directions. So therefore, you need to pay attention that yield strength depends on the polycrystal grain, also textural polycrystal grain. It can be isotropic, it can be anisotropic. Okay? For the example, okay, how you can achieve such kind of case is you can have, for example, cylinder of tandem machine from rolled plate, and then you can correspondingly fire the cylinder towards the target, and then obviously on front you will generate this corresponding highly deformed region. And in this case, right, along the vertical direction versus the horizontal direction, the property will be different. Okay? In the beginning, it is isotropic, but on the high impact, right, then the region that you have is highly compressed along one direction, deformed, but horizontally they have different texture. Okay? So therefore, you can see we are dealing with single crystal, we're dealing with polycrystal, depending on what exact material we're looking at. In most cases, we're dealing with polycrystal. Okay? But we also mentioned that deformation mechanism in metal is mediated by the dislocation, right? So how fast or how easy that dislocation move in the crystal. So therefore, in order to deal with, like say, the strengthening of metals, you have to think about how can I deal with dislocation motion, right? So it's a very systematic, right? In metal, dislocation is this, you can easily have slip of dislocation, right? Moving in the metals, for example, single crystal, polycrystal, as long as you identify the slip system, then you can imagine on a certain load, I will have the corresponding stress, right, apply to those corresponding plane and slip direction, and then up to certain limit, yield strength, right, resolve, that is critical resolve shear strength, then you will initiate the slip of dislocation. Right? So therefore, you will propagate dislocation and generate the class deformation. So what you need to really deal with the yield strength. For example, if I want to enhance the yield strength, all the business you want to do for the conventional metals is to slow down dislocation motion or stop dislocation motion if possible. Okay? Right? This makes sense, right? Yield stress meaning, what's the meaning of yield stress, by the way? What's the definition of yield strength?
The end of the elastic region.
Reaches when you note there's noticeable amount of plastic formation.
Yeah.
Right? Noticeable amount of plastic deformation in metal that corresponding to those generated by dislocation. Right? If I want to enhance the yield strength, what should I do? I want to delay the dislocation mechanism. Right? I want to delay the plastic formation induced by the slip of dislocation. So if I can slow down dislocation, then I can eventually enhance the yield strength. So this is important, okay? You need to keep this in mind because this is the key point for the next or the rest of this whole class. The 4 different strategies for strengthening metal are all dealing with dislocation. Okay? It's not just saying, oh, that dislocation, just line defect, one line or many lines in the crystal is kind of just defect. No. That's the whole point of metals. If you talk to anybody in the metallurgy, right, say in William department, okay, if you say dislocation is just defect, it's not important, then you are basically not getting the point. Okay? So to strengthen metal, to enhance the yield strength, tensile strength, eventually are dealing with the dislocation motion. It's not dislocation density, because in the later case, the 4th strategy is Cold War. Generate a lot of dislocation. Okay? Through generating a lot of dislocation, at the same time, those dislocations get entangled. So it's not about dislocation density, rather about dislocation motion. Okay? You can have dislocation, but you don't want them to move. Or you can have less dislocation, and still you want to make sure they don't move fast or not so easy, right? So 4th strategy, it's weird, within reduced grain size. For example, this is one grain, this is another grain, okay? Of course, in realistic metals, right, you have a lot of grains. And what happens is that if you think of dislocation, right, dislocation is a half atomic plane in the bulk, and moving on the shear, right, moving inside bulk from one to the other side, for example. If a single crystal, once you reach the critical revolve shear stress, that will propagate easily, right? However, for non-single crystal, for example, polycrystal, then you naturally have grain boundaries. Right? If you instead of a single crystal, now you think about one single crystal, another single crystal put together, but form a grain boundary, then we call it polycrystal. Right? With polycrystal, we have grain boundary. Then what happens is that this dislocation, for example, you want to force it move from left-hand side to the right-hand side. If this line, or say these 2 grains are perfect line, what will happen? Easy propagate. Perfect line meaning like as if it is almost like single crystal, right? I mean, this is the corresponding slip plane, this is slip plane, right? However, if I tilt the slip plane, what will happen? It will be very hard for this half atomic plane to move and rotate, switch direction to the other plane. So therefore, through this mechanism, you're basically saying, I want to create barrier for dislocation moving across the grain boundaries between many, many grains. Even though dislocation can be generated, can be propagated inside the grain, but when they try to move across different grains, right, they have hard time because dislocation, half the atomic plane need to rotate direction and go to another crystal. Right? They need to overcome this barrier. This is the so-called, eventually, if you try to say, okay, if I think about, right, the grain size, right, in the single crystal, the grain size is what? Diameter is what? If in the perfect single crystal, what is the diameter of crystal? What is diameter of this corresponding grain? It's the size of corresponding grain. But if I cut them into many pieces and then reorient them, then form a lot of grain boundaries, then corresponding grain size will reduce or increase? Reduce, right? If you reduce, and at the same time you create a lot of grain boundaries, a lot of barriers, right? and further cut them, and then rotate them, think about, right? And you create even more. So what happens eventually, the yield stress is very famous Hall-Petcher equation. What is essentially saying, the yield stress, if you try to plot, in a single crystal case, it's much easier to move. So therefore, the yield stress of will be something like 4. This is, right? If you have stress, strain, right? Typical metal, like say, yield stress, right? And then break, right? And then you can determine what is corresponding yield stress, right? 0.002, right? This is determining what is corresponding yield stress, right? Sigma 1. Okay, in this case, let's say this is single crystal. Okay, single crystal meaning the D go to infinity. Okay, now you think about, instead of single crystal, you try to break them, make them into different pieces, different orientations. Right? Orientation is different. Then you generate a lot of green boundaries. Instead of, in this case, you have perfect single crystal. Right? The size is the same, but diameter reduced. Right? So therefore, what you are going to expect is that this way going up and going down. Okay? So therefore, the yield strength will enhance. If I have the diameter, if I reduce diameter, if you go further and further, you're going to see that even enhance more and more. Okay? This is when you reduce diameter from infinite single crystal to smaller and smaller grains. Okay? And so therefore, if you plot this corresponding yield strength as function of diameter, then you will find out this following relationship. Okay, that yield strength is equal to some constant plus corresponding ky and 1 over square root of d. Okay, this is very important. It's not square root of d rule. It's square root of d on the denominator, right? And the ky. This is y at any specific diameter. Okay, so the d, if we reduce the d, this factor becomes much larger, and then yield strength is enhanced. Okay?
So does the ductility also tend to fall as yield strength increases at these type of
Yes,
constants?
very often, yes. Okay? And so this is just one magnet. You can clearly see. And if you check, this is a very famous equation. Even a lot of research nowadays, when people are trying to perform all kinds of fundamental research or realistic, like say, industrial application, they're still referring to this equation. Okay? And this is just one example to show you that you can enhance, like say, strengthen the material, right? Increase the yield strength by correspondingly reduce the grain size. Okay? Because you create a lot of diagrams. Now, second one, okay, is so-called solid solution strengthening. In the previous year, you reduce the size and create a green one. Here, idea is that you try to embed, so these are the original lattice, but I try to embed the defect into the lattice. For example, through impurities or solid solutions, right, with different size of atom. Then what happens is that whether it's small or big atom, they will generate local stress field. If you think about it, you have this location, right, half atomic plane coming from left, moving across the local region around the B atom. What happens is that the local stress around this atom, for example, at the left top corner, have a counter stress field to the motion of this location across this region. So therefore, this location will have hard time to move from left to right. However, if you look at this particular position, then stress field is pointing to the right-hand side. So this location can move in this case, we'll try to move to the right-hand side here, but the problem is that on the bottom right corner B point here, you have stress also counter to the corresponding dislocation. So therefore, the key is that have these, for example, impurity atoms with different size generate a lot of stress near the atom. Then what happens is that when dislocation comes through around this local region, you will slow down the dislocation motion, right? Obviously, you need to have significant amount of impurity, right? You cannot have, say, just 1 out of 1 mole, right? 1 atom out of 1 mole embedded as impurity embedded inside the matrix, and said, oh, I'm going to use 1 single impurity atom to like enhance or strengthen the metal. You cannot. You still need to have significant amount, not 50%, but at least like few percent, for example, right? To introduce a lot of stress field inside the matrix. Right? It's like create a lot of bumpy. Instead of have highway, you create a lot of bumpers on the highway. Right? It's exactly like that. You still dislocation can still try to push through, but by making a lot of bump on the highway, you cannot drive car fast, right? So therefore, it's the same thing for dislocation. They have to slow down. Okay. Now the second message is that you may think you need to always have large impurity atom. The answer is wrong. Okay. You can have small or large, both can be effective. Okay. Because the difference is that whether you create, for example, in this case, right? You create a stress, counter stress field on the left top corner or on the right top corner. So in either case, they will slow down. Okay. Now, if we look into more microscopic picture, we look at the exact stress field around dislocation, what's going on, and we already learned, right? In the dislocation, like edges going on top here, for example, it has a lot of compressive stress, right? And compression. And here, I have tensile stress. Right? So if I have a corresponding atom, right, through soil strengthening, for example, the small atom, they tend to go to this area because through small atom substrate here, they can release the stress easily. If I have big one, they can sit on the bottom and release the, since there are a lot of open space there, right, there's fitted atoms over there, then in this case, then I can correspondingly slow down dislocation when it crosses the corresponding area. Okay, so this is a website that is free to everyone. You can access by click this link. I hope it's still active. I also think so. You can check. Okay. What happens is that this gives you a basic like there's a movie showing, you know, dislocation moving from left to right, and what is corresponding stress field there, and how the solid solution strengthening is activated. Okay. So take advantage of resources, even though there are so many slides I'm trying to convey in the class, but still these resources are very useful if you don't have the picture. Okay. Here is one example. Okay, like the previous case here, for patch equation, you also can have an empirical equation like the following: U strength is roughly proportional to the square root of concentration, which means if you try to mix that the solid solution, right, the U strength can be enhanced. Okay? And at the same time, if you look, for example, here, strength, tensile strength versus the concentration of nickel, right, in the put into the copper, what happens is then the tensile strength will be enhanced. Okay. Okay. There's another one. Right, besides reduce the grain size to create a lot of barrier because of the grain boundary, right? Or you create a lot of local stress to counter dislocation motion, slow down the motion by those solid solution. There's another one, so-called precipitate stress. So what is precipitate strengthening? Right? In the previous case, you always try to create a trouble for dislocation to move. The same thing here. You put the precipitate so that those precipitate, for example, very often is those very strong or hard precipitate, such as silicon carbide, those ceramics. Put inside iron, put inside aluminum. What happens is that those silicon carbide, they're very, very hard, right? They're ceramics. So when dislocation try to come through, what happens is that for dislocation to move across, in principle, you have to break the bonds, right? If you have perfect ceramics, for the one atomic plane move from left to right, you literally need to shift this corresponding plane, right, top plane, by at least one Bourke's vector, right? You need to literally break the bonds and reform, break bond and reform. So eventually, you should, in principle, if you really want to push the dislocation through, you need to form this shape. But this is very, very hard. You know that, right? In general, that means you need to apply very large shear stress to generate such kind of deformation to ceramic. And this is very hard. Right? In metal, it's easy, right, from those dislocations. But this is very hard for ceramics. Right? So because of this mechanism, so therefore you can think about you have multiple dislocations, precipitates inside this matrix. These are matrix, white area, and these are precipitates. Then what happens is that in the beginning, I have this location line, like half atomic plane, moving from bottom to bottom up, okay? And then what happens is that dislocating quantities corresponding precipitates, dislocation line can deform. However, they can deform around this area and then moving across, but the one here, they cannot. Okay, because you really need to have huge shear force to basically try to break the bonds in the ceramics. That is too hard. So therefore, what happens is that you will see the dislocation will basically deform but will not cross and will slow down. Okay, so this basically creates a lot of trouble for dislocation to move around the precipitates inside the metals. And again, there's an empirical result. What happens is that if you consider you have a lot of precipitates, the average distance between each precipitates, average distance between two precipitates is, for example, S. Okay, then the yield strength will be enhanced if you have a lot of precipitates and distance reduced, for example, from much larger distance to small distance, then yield strength is scaled as 1 over S. Okay, so if you have more and more precipitates, then yield strength will increase for that. So these basically give us different ideas of how you can strengthen the metals, right, using different methods. Again, everything is dealing with what?
Dislocation. Right.
Dislocation,
Motion.
Very, very important. It's dealing with dislocation, motion. Not just dealing with dislocation. Dealing with dislocation, yes, it's partially true, but the next example I'll show you, people can even create a lot of dislocation to strengthen it. It's kind of weird, right? Here we are having a lot of dislocation moving, right? But we're not dealing with dislocation density. We're dealing with dislocation motion. Okay, so this is very important. So here's one example that people are already using, right, back to a long time ago, using the precipitates to strengthen the, for example, aluminum. Right? Because aluminum is light, can be used in those airplanes, like, right? You don't want to carry a lot of iron in space, right? So therefore, aluminum is very ductile. How can you strengthen it? Or use strength low, pure aluminum. So because FCC easily yield a lot of slip system, top slip system, right? So in order to strengthen it, right, use strength, enhance it. People are using those precipitates, for example, silicon carbide, etc. Okay. Now this is the one that I was trying to emphasize. We're dealing with dislocation motion. That's the key, okay, to complete sentence, to state the key mechanism key. So this is so-called string hardening, okay? It's or code work, okay? So basically what is code work or string hardening? Essentially it's the deformation, through the deformation at the room temperature, for most metals at room temperature, you can strengthen the metal. Okay, be careful. Cold is not minus 100 Celsius. Okay, it's not that cold. It's just at the room temperature. Cold because compared to a lot of heat treatment, it is at room temperature, it's red, and without applied heat, right, at the room temperature. So it's not that cold, it's just room temperature. Okay? Compared to metal, the melting point is very low. So, for example, you can consider a lot of different engineering practice. It's kind of boring, but it's very effective. Okay? Like through forging, through drawing, or through rolling. Again, you can through extrusion. Basically, you try to deform large amount of metal through those machines, right? Machineries. And basically, you can measure the amount, for example, through drawing, it's easy, right? 2 die, and you fix. And here on the left-hand side, you have metal, and try to squeeze through. On the right-hand side, you apply pull, tension to pull it. And what happened initially, on the left-hand side, you have larger diameter, right-hand side, small diameter, right? So after drawing, you have small diameter. So therefore, people use the same for other cases. So therefore, people can quantify percentage of code work, okay? Which means the this corresponding work that they apply by the percentage of area reduction. Sorry, okay. So this percentage, which means the area reduction, delta area, right, the area change with respect to original area times 100. Okay, this is percentage. Don't forget this is percentage. Right? Why times 100? Because already left hand side percentage. Okay, so this is the corresponding code work that routinely applied in industry. But why this is related to dislocation? Well, we're saying applying code work, but why this is related to dislocation? The thing is that you can think about that. On the left-hand side, probably it's like relatively large grain or single crystal, for example. Usually it's not single crystal, but larger grains. Without much dislocation. Okay, density. But through this mechanical deformation at room temperature, you're generating a lot of dislocation, okay? You're generating a lot of dislocation metals through the code work. So this is dislocation structures, those black lines, dark lines here, right? And those are the corresponding dislocation structures in titanium, okay? After code work. Okay? It generates dislocation. But the key is that these dislocations are entangled with each other. Right? If you think about, sorry, I borrowed this kind of way, right? It's like initially you don't have dislocation or a very low dislocation. And now you try to make a lot of strings in in the metals. However, those strings are not aligned perfectly, so that you can push through. Rather, because you have a lot of grains along different directions, so when you generate dislocation, they are not specifically aligned. Okay? Then after this extreme code work, you're expecting a lot of dislocation, just like a thread. You can think about it, right? They mix together. So what happens then? You form entangled structure. Therefore, like form a knot or whatever, they cannot move. There are still some of them, they will interact, maybe annihilate, whatever, but a small amount. Since you're applying a lot of code work, so you generate a lot of dislocations. At the same time, because it's kind of random, you can think about it like a very, right? You definitely have your like life experience with strings, for example, put together, right? If you smash it and then try to, like, right? For example, those cables, right? Very often you need to spend a lot of time to sort it out. The reason is because they're entangled. There are a lot of topology inside the thread, right? Inside this one dislocation here. So you need to untwist or disentangle those corresponding dislocation. And that will be hard, right? You can do it in your real life, right? Since it's just short string, you can do it by hand, but for bulk, right? Or metals, so many dislocations, they cannot. So therefore you have a lot of dislocation. It's kind of counterintuitive, right? You want to stay away from dislocation. Looks like you want to stay away from it. But what happens is that you're not just dealing with dislocation itself, you're dealing with dislocation motion. Okay? By generating a lot of defects, but those defects cannot move, and that's fine. Okay? For example, here, if you think about dislocation density, by the way, what definition of dislocation density is the total length of dislocation, because dislocation is line object. right? So you measure the line, dislocation lines, right? The length of dislocation, total, I mean, imagine, right? If you sum all of those lines, the length of those lines, right? For all dislocation, imagine inside out, divide by total volume, right? The volume of this whole chunk of titanium, for example, uphill. And that is corresponding to dislocation density, okay? So therefore, dislocation density has a unit of what? 1 over area. It's reciprocal of area, right? Because the length divided by volume. Now, check out this form and these numbers. Carefully grow single crystal, even though it's not perfect, but the density is around 10 to the third, which is 1,000 per millimeter square. But after Cold War, okay, very often you can reach 10 to 9 to 10 to 10, which is 1,000,000 times of the original, 1,000,000 times of original density. There's a lot of dislocations packed. Right? These two probably can clearly see, right, the reason why we're emphasizing. There's a weird part here, I mentioned here, heat treatment. You can do heat treatment, basically try to move the circuit around. What happens is that they can annihilate from initially calf-grow single crystal, put in this Cold War, extrusion, whatever, forging, you generate 10 to the 9 to 10 to the 10 per millimeter square dislocation density, right? From very low to very, very high. What happens is that I can also do heat treatment to lower dislocation density from 10 to the 5, 10 to the 6, back also so to 9 to 10, to relatively much lower dislocation density. Oh, even though it's still higher than clinical, it's still much lower. Now, there's a reason why I want to emphasize this. There's two reasons. First of all, when you generate a lot of dislocation through Cold War, at this particular temperature, they will not annihilate to each other easily. Okay? They will not have strong interaction, so that will reduce density. But Cold War will, heat treatment will move the dislocation through different mechanisms we are going to mention, and eventually reduce the density. Why do we want to, starting from single crystal, to generate lots of dislocation by Cold War, then do heat treatment? There's a reason. The reason is because in industry, if you want to make materials with specific properties, you are not only emphasizing the yield strength, you also want to achieve corresponding, for example, the ductility. Right? You not just do one step, you want to do multiple steps to achieve a combination of nice property given certain constraint. So therefore, what you need to do is that you need to do Cold work, right, and deform the, for example, sample shape, and then do heat treatment, go back to relative original property, and then do another Cold work so that I can reach the range of materials property that I want. So I will show one example in this class, okay? So what will happen for heat treatment, or what is governing also the corresponding the sample after Cold work, okay? The key is, again, coming back, think about, right? If you have two dislocations, a lot of dislocations, then you will have high chance to have two dislocations with same sign, which means half atomic current here, half atomic current here. And then you have repulsive stress between these two dislocations when they are adjacent to each other. Of course, closer, higher repulsion between these two, and if further away, then less. Right? There's another possibility that you can have on the upper plane have half atomic plane. Here you have another half atomic plane. In this case, they have opposite stress. And what happens is that these are actually attractive. Okay? So half atomic here, half atomic here, then we'll eventually, for example, if it's a perfect line, and move towards each other through this attraction. And what happens in the end, they will form perfect atomic plane instead of half atomic plane, because the half put together, they form a single crystal plane, right? And therefore, they form perfect crystal. This is called dislocation annihilation. Okay. So in cold work sample, you have so high dislocation density. So therefore, you have a lot of scenarios that will have dislocation that is in under highly repulsion case. So dislocation cannot easily move across each other. And the second, when you do heat treatment, this is for a lot of like cold work sample. But for heat treatment, what happens is that you may move dislocation around and then make them align. Okay, that we are going to show in the next list. But let me use this slide to emphasize the impact of cold work. The same material with low carbon steel, okay? But you apply, like initially this without cold work, okay? As you can see, the yield strength somewhere right here, okay, around 200 megapascal. Be careful, yield strength is not Young's modulus. Young's modulus at uniform metal around gigapascal, tens, hundreds, thousand gigapascal. But for the corresponding yield stress, right? It's at a megapascal, 100 megapascal. Okay. Let me emphasize one more time. And then if you apply cold work, for example, just 4% cold work, what it means is, for example, through this extrusion, that the area reduction is just about 4%. They are going to see that yield stress already enhanced from 200 all the way, for example, around 400. However, of course, if you look at the ductility reduced, okay, this ductility is relatively high. And if you continuously apply it to 24%, right, for example, instead of 4%, apply 24%, then you can even enhance to higher yield strength, right, around like 550, for example. So therefore, if you look at it, the yield strength will increase when you apply cold work, more and more cold work. And correspondingly, the tensile strength also increase. Okay, tensile strength also increase. Don't forget what is tensile strength or ultimate tensile strength. It is the highest strength that can reach during this stress strain or on this stress strain curve, right? And ductility will reduce. Okay, so ductility from here around like very high corresponding plastic strain to relatively low plastic strain. Okay, so here is just one simple example to show that how you can utilize these informations. For example, in industry, right? If there's some certain table to tell you with percentage amount of like cold work, what is corresponding change in terms of tensile strength or yield strength or ductility, right? Then you can use those information established in the industry to design, for example, or calculate what is the corresponding yield strength or ductility, etc. Okay. For example, here you start with like this is a carbon rod and cylindrical one, right? And you have diameter around 15.2 millimeter. And after cold work, for example, extrusion, etc., right? You form diameter that is reduced down to 12.2 millimeter. And can you calculate what is the corresponding cold work amount first? You can do that, right? Very easy. Just the area. Pi r square, right? Difference between this one and this one. So you look at the area, reduction divided by original area here, right? And then times 100, that will give you the corresponding percentage that is equal to 35.6%. Okay, which means the area reduction is 35.6%. With this number, what you can do, you check the table for the copper. Okay, specific power, what is the property of corresponding yield strength versus amount of cold work, tensile strength, amount of cold work, or ductility with amount of cold work. Okay.
These are all empirically, are these graphs generated empirically? Like
No, from a lot of experiments.
Yeah.
Okay. Yes.
Yes. Sure.
Okay. So therefore, now you plug in the one that you calculated, right? This is the, for example, if you are designing certain process, right? And this is, you apply the 35.6%, right? And you check what is the yield strength, what is the tensile strength, and what is the ductility. Looks like very straightforward. We haven't dealt with any heat treatment yet, right? Let's look into more details, okay? This is just one example, say, given fixed amount of cold work, what are you going to achieve? But as I said, in industry, when you really apply this metal processing, try to form specific shape and with designed ductility, right? You don't want just a very high yield strength but low ductility. So I want to have a certain set of nice combination, right? But however, you know, starting this original shade, if I give you a raw sample you bought somewhere, right? And then what will happen is that if you just apply one step, you have always fixed the property. If you, for example, reduce from 15.2 to 12.2, if you only apply one step code work, you will always, with fixed amount of code work, you will always get exactly these 3 points. It may be changing from here to here and other places, but it will be exactly 3 numbers, right? If you apply just one code work. However, in industry, obviously, you want to achieve maybe better ductility. I can sacrifice a little bit, use strength. But how can I do that? You cannot just apply